Today we're going to do test review and induction. So we'll be talking about logic and predicate calculus and logic circuits. And then we'll do a little bit of review of set theory, and we'll get started on some things that we need to know to do induction. You have a question, Brian?
Yes.
Yes.
Are the answers available for the old test?
No, the answers are not available for the old test. But you can work on them with anyone else, and you can also come to office hours and ask us to help you work them.
Is that theory on the test? Not, is it?
No, set theory is not on the test. Other questions? Yes.
When is the tutorial due to be turned in?
You'll have about 2 weeks to do the tutorial. I recommend doing as much as you can before the test. Okay, so first let's start from the beginning and review logic. So what is a proposition?
Statement. Either true or false.
It's a statement that's either true or false. And what are our logical operators?
And or
Not.
And, or not, implies, and exclusive or. And what's the main thing to remember about and?
both are true.
So if P and Q is true, then both P and Q are true, and that gives us which rules? Simplification. And the conjunction rule also comes from the definition of and the way we do formal proofs. But the most important thing to remember about and is that when I take two variables, two binary variables, and I AND them together, and preserves the zeros. Right? So it's like times because it preserves zeros.
It was simplification in what?
Simplification and conjunction are the two rules that go with and. So with or, how does it act?
Addition.
It acts like plus, and it preserves what?
Truths. One.
True.
True values or ones. And what are the rules that have to do with or?
One or the other is true.
The apple-orange rule, right? Disjunctive syllogism? What does disjunctive syllogism say?
If one is negative, the other one is true.
Right, that's basically it. So if I have an apple or an orange, and I tell you I don't have an apple, then what?
You have an orange.
That means I have an orange. And that's how I remember disjunctive syllogism. Okay. With implies, what is our basic definition of implication?
Not
Less than.
less than or equal to.
I can think of it as less than or equal to, but I could also think of it as what? In terms of logic, I can think of it as not P or Q. This is the one that I really think of as the basic definition for implication. So P implies Q is true when either P is false or Q is true. So if I tell you if it rains, I'm going to get wet, then either it didn't rain or I got wet. So this has a lot of rules that are associated with all of these definitions. The first one is the implication rule, which is this one here, that says that P implies Q is logically equivalent to not P or Q. Then we have modus ponens. What does modus ponens tell us?
P is positive or true and Q is false.
If I know that P is true and I know that P implies Q is also true, then I know that Q is true. And I think of this rule as, if I know if it rains, I'm going to get wet, and I know it's raining, then I remember that I must be getting wet. Okay? This is very similar to disjunctive syllogism. Why is that?
Because with syllogism, you know that the first one is false, so the second one has to be true. And in here, you know that if the first one is false, the second one has to be true as well.
So the reason is because an implication is like an or, and disjunctive syllogism combines knowing something about one of the variables with knowing an or statement and being able to eliminate one of the variables, and that's exactly what happens with modus ponens. So let's prove modus ponens with the disjunctive syllogism. So if I have P implies Q is given, and I want to prove modus ponens with disjunctive syllogism, then I also need to have P is given. And modus ponens means if I knew both of these, I would know that Q is true, right? So let's prove Q. So if I'm not allowed to use modus ponens, what would be the next thing you would do?
Not P or Q.
I would use the implication rule to change P implies Q into not P or Q. So that would be from line 1 and the implication rule. So now what would I do?
You would say
Simplify.
simplify and...
Can I simplify an or statement?
Sorry. You would combine
good.
2 and 3
Yes,
You
to
don't
say
want to
that
do that.
you combine 2 and 3 to say that Q is true.
And that would be with disjunctive syllogism. So this says I either have an apple or an orange. So I have not P or Q. This one says that not P is false. So I don't have that apple, so I must have the orange, so Q must be true. So I've just proved modus ponens using disjunctive syllogism. What does modus tollens tell me?
If you have not P, then not Q.
If you know the conclusion.
If I know P implies Q is true, let's look back up at this proof. If I wanted to know something, instead, if I know something about Q, I could figure something out about P. So if I look at this or statement, not P or Q, what would I need to know in order to get something true about P?
Not Q.
I would need to know that Q was false in order to cancel it out. So modus tollens is just like using implication rule, only it knows something about the Q. It knows that Q must be false. So I have that Q must be false, and I can conclude from modus tollens that 3 would be that P is false. So if that were given, then lines 1 and 2 together would give me modus tollens would give me not P.
P for positive, meaning that you know that P.
And I could do a very similar proof for modus tollens as I did for modus ponens. It would be exactly the same, except line 2 would be not Q and line 4 would be not P. What are some other rules that implication is really good for, or you use with implication?
Would contrapositive count?
Contrapositive is a really important one. What is that one?
It pretty much gives you a way to reverse the sign of the.
It lets me reverse the order of the implication and negate both of the variables. So if I have P implies Q, then I know not Q implies not P. So if I have P implies Q and I negate that, could that possibly be equal to this?
No.
It can't, because remember that implication is an or. If I negate an or, I'm going to get an and. So I can't have an or on two sides of a logical implication. So these are not the same. So anytime you want to do De Morgan's, you have to have either an and operator or an or operator.
So is P and not Q the same as P implies Q?
That's right. So not P implies Q is the same as not the quantity, not P or Q, using the implication rule. And then if I use De Morgan's, that's P and not Q. So if this were given, then I would have used line 1 in the implication rule for that. And for the last one, that would have been 2 in De Morgan's. And what step did I skip?
Double negation.
Double negation. Good. What could I do next after I knew P and not Q, supposing this was a longer proof?
Separate, simplify.
I could simplify because that's an and. So anytime you see a not quantity P implies Q or any kind of implication that gets negated, you know that once you negate it, you should get an and, finally, and you should be able to do simplification. Yes?
On number 3, if we wrote it just like that, but we also had double negation next to De Morgan's,
That
like
would be
De Morgan's
fine.
and double
That would be
negation.
fine.
Yeah.
On the proofs tutorial, you can't do that.
Right.
But on your paper, I don't mind if you just note to yourself that you also use double negation. Okay, what's another very important rule that uses implication? What is everybody's favorite rule?
Hypothetical solution.
You all forgot. Lonely little rule out there. Hypothetical syllogism. And this one tells you what?
You can have a variable.
If I know P implies Q and Q implies R, then P implies R. So in a proof, I would have P implies Q on a line, Q implies R on a line, and I would have P implies R on a conclusion line. So that lets me get rid of a variable also. So those are the main rules that we use for implication, but there's one more that's very cool. And what is it? Constructive dilemma. And this is really my favorite rule. Takes a proof and makes it really short. Like I said, I don't mind if your proofs are long, but constructive dilemma can really help you save a lot of work. So what does constructive dilemma do?
Takes the first of 2.
So basically, just to remember it, it combines 2 implications and gets a new one.
So it would be P or Q implies Q or R.
So I could take, if I had P implies Q and R implies S, then that would give me P and R implies Q and S, or I could get what?
Or
P or R implies Q or S, as long as I have the same operator on both sides. So I combine the left-hand sides on the left, I combine the right-hand sides on the right. And this is the same kind of thing that we do with less than or equal to all the time. So if you had 2 less than or equal to's, you could add the left-hand sides and add the right-hand sides, and you would still get a less than or equal to that was still true. And you could do the same thing with multiplication as long as you were sure there were no negatives. Right. But we don't have to worry about that in logic because we don't have any negative values for our truth values.
How does that make a proof really short?
It makes a proof really short because suppose that, let me give you an example of a proof. If I had to prove Q and S, then if I know P implies Q and R implies S, and I also know P and I also know R, then I could make this proof pretty short by saying all these are given. I would say P and R implies Q and S, and then I have Q and S together, right? And then all I have to do is get P and R, and then I'll be done, because then I can use modus ponens. So 1 and 2 in constructive dilemma will combine those 2 lines, and then 3 and 4 I can put together to get P and R with my what rule?
Conjunction.
So with 5 and 6, I can use modus ponens and get Q and S. I could have used modus ponens and got Q from one line and got S from another line and done conjunction. But in some other proofs, you might not have something as nice as this. But this was a simple example I made up. But constructive dilemma lets you combine things a lot faster. So there's the whole proof there. So if you see that you're proving something and you have two variables that you want together in the proof statement, and you've got two implications that have those two variables, you can use constructive dilemma to put them together on the same line. And then you know that all you have left to do is get rid of the variables that are on your line that you don't want. So that brings me to leading us through the rules for doing proofs. So let's talk first about direct proof. What's characteristic of a direct proof?
All the statements are true.
I assume that my givens are true, and I want to end the proof with the statement that I'm trying to prove. So the first thing I do is I write my givens. Then I look at what I'm trying to prove. I'll just say that's my conclusion C. Then I find a line in the proof that what?
Looks like what you're trying to prove.
Looks like C. And looks like means has the same, at least one of the same variables in the same kind of format. So if I have P implies Q, I would look for P implies something. Or I would look for not P if I didn't have any implications. Why would I look for not P?
Because you can put not P and it together with something else to get an implication.
Because if I had P implies something, then that really means that I have a not P or something else. So I'd be looking for not P if I didn't have any implications that had P in it. Okay? So then what I do is I try to eliminate variables. So let's call this line A. That gives me line A, step 3. And then eliminate variables on line A that are not necessary. So they're not in C. So what are my rules for eliminating variables? Hypothetical syllogism, right?
Disjunctive syllogism.
Disjunctive syllogism.
Modus tollens.
Modus ponens,
Modus tollens and modus ponens, those are the main ones. So in order to eliminate variables on a line, I have to look for a line B that has the opposite of variables that are in line A, right? So I would have to, in order to use these rules, I have to have one other line to combine with line A. And I would look for ones that would help me cancel variables. And then I would repeat that until I got my proof line. So 5 is repeat until done. What are some intermediate steps that you might need to do in order to do these things? If I want to use hypothetical syllogism, I have to have two whats? I have to have two implications. So if I have two lines to combine, then I need to make sure both of them are in implication form in order to use hypothetical syllogism. So one of the first things I do when I get a proof is if I have some implications and some ors, I switch all of them into implications. And why would I use implications instead of ors?
Because ors are difficult to simplify because
That's right.
one or the other is.
Okay, how many pages of rules did I have to do that had to do with implications? Like 4 or 5, right? So I had one rule that was associated with or, which is disjunctive syllogism. So I don't have a lot of tools to combine lines with ors. I have a lot of tools with implications, and they're simple because I won't mess up because I know the left-hand side does something and the right-hand side does something, and the order matters. And if I keep track of doing everything the right way, I won't get confused. When you have an or, it looks kind of like an and you might forget and do simplification. And also, we don't have rules that combine two lines and eliminate variables. So suppose that I had this. This is a problem that you see a lot in proofs. If I have not P or Q, and I have P or R, I'd like to combine those two lines and get what?
P and not P. P or not P.
Q or R would be what I would like to
Q or
get,
R.
right? You can't do it. There's no rules that tell you can do it. You would have to do a lot of mess to do it. How would you do it? Anybody know?
Convert them to ands.
You can convert them into implications. P implies Q, and then
Not P implies R.
not P implies R, so that would be 1 and 2, and both of those are implication rule. And then 5, I'd have to do contrapositive to reverse the order so I could use hypothetical syllogism, right?
Couldn't you do the
I could do constructor dilemma and get P and not P implies Q and R, but that wouldn't be the one I would do just because it would require some extra steps. I'd rather use hypothetical syllogism here because then I have to show that this is 0, and then I would have to say if 0 implies something.
But if you use ors,
If I use ORs, this would be 1, but still I don't have a good rule for doing that. So I would use I would use contrapositive and then do that. So I would use not R implies P from line 4 and contrapositive. So this is still okay. This is still fine. But I would do this because hypothetical syllogism is my favorite, and then I get not R implies
You wrote P.
Q. I wrote P. Said R, wrote P. Okay,
So line
that's
5's not in there though, right?
it's in there. You just don't use it. So this was 3 and 4 and constructor dilemma. I know you all have written proofs where you put lines in that you don't use. Come on, everybody's done it.
What does line 7 say?
Line
Not
7
R.
says not R implies Q. Sorry, I wrote the wrong thing. So
What are you trying to prove?
Q or R.
Proving.
I was trying to combine lines 1 and 2 to get something interesting.
Like.
Q,
Q or R.
Q or R is kind of where she set off to go.
You should have been listening, Simon. I said if I wanted to combine these two, what would be something that you think would be true from these two? I'm trying to head off errors that you guys make. That's what I'm trying to do. So if I wanted to prove what would I be proving? That's what I asked the class, and people said
Q or R.
Q or R.
No, he said.
Okay? But you can't just take these two and write Q or R and say that was my fancy rule that I just made up. Okay, because there aren't any rules that do it. So that's why we were doing this. This one is not R implies Q. It looks way worse on the overhead than it looks here. Okay, so that was from what?
Hypothetical solution.
3 and 6
3
and
and
hypothetical syllogism. Okay, and then I can change this with my implication rule back into R plus 2, which is almost the same thing as that. And how would I get it exactly the same? Commutative.
Commutative.
So is there a rule for if one implies something else, that something else is true?
No, there's no rule for that, but there is a rule called absurdity that if you have something implies a 0, then the hypothesis is false. That's called absurdity. There's not one for the other, but you could do contrapositive and then use it. So the question was, is there a rule that says if I have 1 implies P, can I write P on the next line? There's no rule that says that, even though it's true. So
So I
I've
can't
given
do
you
it.
an axiom list. You can do it. You just have to do it with more steps.
Oh.
I would have to say not P implies 0, and then write P. So this will be, this is contrapositive, right?
Sure.
I negate both sides and change the order.
Okay.
And then I can conclude P from 2 and absurdity. It's just that people hadn't used it, that's all.
Okay.
And there's lots of rules that we could make and add to our axiom list. So The idea is that you have to be able to use what you have. If I told you you can only use 5 rules, then you would have to figure out how to do your proofs with just those 5. And it's good to do that because then you really understand the logic behind everything.
So for the test, are we going to have one big, complex, tough one, or are we going to have a bunch of smaller ones?
You'll have several not so hard proofs to do. And you'll have a fill-in-the-blank proof. Just like on your homework, you can have very similar problems to your homework problems and last year's test. Okay, so we talked about direct proof. So the main thing in direct proof was to keep focused on the conclusion, on what you were trying to prove. Trying to get the variables that were on there and then eliminate the ones that weren't. All right, so for indirect proof or proof by contradiction, what's our steps there? Our first step is write the givens, as usual. But then what?
Negation.
Negate the conclusion.
Simplify negation.
And we want to apply De Morgan's. If we can, we have to do implication rule if it has an implication, right? But our goal is to do De Morgan's and then simplification on the negation of the conclusion.
Isn't it always going to have De Morgan's because you're negating the conclusion?
Well, you may not have to if you have, like, P is your conclusion and you put not P. You don't have to do De Morgan's on that, right? That's as simple as it's going to get. So if I were trying to prove P implies Q and I had put a not in front of it to make the negation of the conclusion, I would first have to use what rule? Implication rule, and then I could do De Morgan's. So De Morgan's only works on ands and ors, so I have to convert anything that's not an and or an or into that in order to do De Morgan's. Okay, so that gives us some money, right? And we can label those lines as money to remind ourselves that those are the things that came from the negation of the conclusion. And what is our final goal in proof by contradiction?
Get something and not something so that you have a contradiction and get 0.
We want to find 2 things that are opposites that we can AND together to get a false. Because if we get a false, we assume it must have come from that negation of the conclusion. So if the negation of the conclusion is false, then the conclusion must be true. And that's why. So our goal is to get 0. So we spend our money at the store, and where's the store?
Givens.
Givens.
That's the given. So if we feel like we don't know what to do next, just make sure that you've combined all the pieces that you got by negating the conclusion, all that money that you labeled, make sure that you've combined it with the givens and that you've used them. And if you don't know where to go next, try combining whatever's left that you haven't used yet.
A good way to keep that is put a check mark when you use a line.
That's right. I usually check a line once I use it. Check a line if you've used it. There's only a few proofs that once you've used a line that you might have to use it again. Sometimes you do. There's one on the tutorial that you're going to have to do that with. I actually haven't figured out a way to do it without using one of the lines twice. I haven't sat down to really, really do it, but every time I've written that proof, it's proof number 4 on the proof tutorial. I've always had to use one of the lines twice. So.
But specifically, if you're going to do it by negation.
Just by direct proof. I'm not sure about on proof by contradiction. So if you check out a line, if you've used it, then that'll help you remember what you've already done. Because our goal is to find any 2 things that are opposite, so it's kind of confusing if you've got a lot of lines there, and always to be checking them. So it's good to mark which ones. That's why I mark my money, and I go back to the givens and combine it. And then as soon as I've used them, I mark them out and I label my new money, the stuff I got that I bought at the store with my money. So what are the rules that help me combine things that I might get from the negation and conclusion with things that are in the givens?
Simplification.
Especially good stuff is modus ponens, right? Like, say that I have in a given P implies Q and I get P as one of my money. I can get Q right away. right? And if I get not Q, then I could get not P right away. Okay? So this is another place where constructive dilemma might help you, because if you had in your negation of the conclusion, if I ended up with something like not P and R, and I had, let's see, so if I had Q implies P, R implies S, and not P and R, and these are my givens, and this was after I did lots of stuff with my negation and conclusion. I meant to do an or there. Let's do an or. Because I would have simplified even more if I had an or. Sorry, if I had an and, I would have used simplification and not ended up with this. So this is my negation and the conclusion after I've done stuff to it. So I could use constructive dilemma to get the P and the R together. But first I would use contrapositive to get not P implies not Q, because then the P would be in the right form. I would have a not P. So from line 1, I would use contrapositive. And then on line 5, I would put them together. So I would get not P or R implies not Q what?
Or S.
Or S. So that would be from 2 and 4 in constructive dilemma. And then on line 6, I would know what? I did this for a reason. Right? So this was my money. This was the store. I used both of the lines now.
Cash 3 into 5.
I haven't spent my money yet, right? So I'm going to use it to get
Not Q.
Not Q.
not
or
Q
S.
or S. And that's how constructive dilemma can save you some time, because if you know you need to combine this piece with your givens, and you can put some of the implications together in order to use modus ponens, then that's very convenient. So 3 and 5 together and modus ponens gave us not Q or S. And that would just be part of a proof. That's not a complete proof. I was just showing you how constructive dilemma could be useful when you're doing a proof, even a proof by contradiction. What is a very quick way to do a proof by contradiction if you have a direct proof? If you've already done a direct proof, how do you do a proof by contradiction?
Just insert the negation of it.
You just put the negation of the conclusion in, because if you've done a direct proof, say you're proving P, direct proof has what on the bottom line? Has P on the bottom line. Negation of the conclusion will be
Not P.
not P. So if I write my direct proof and then I put the negation of the conclusion right under it, I can immediately do what 2 steps that need to be at the bottom?
Put them together. And them together.
So this is what I'm saying. So if I had, say, I had 10 lines that proved P, and on 11, I was like, well, someone told me I had to do proof by contradiction, so I put negation of conclusion. And then I could do conjunction, which is a required step in proof by contradiction. And then I would put 0, because P and not P is always false. It's a contradiction. And so that would be from line 12 and the contradiction rule.
So you saying on homework 1, where you wanted us to prove it was by direct and contradiction, we could have done that?
Yes. I did say that in class before, too.
Yes.
Just in case. Like, if you're having trouble doing a proof by contradiction and you're better at direct proof, you can do a direct proof and then do that. But doing a proof by contradiction probably won't help you doing a direct proof, right? Because in proof by contradiction, I put something false into my proof, and so it's not going to help me write only true steps for my direct proof. What is wrong with this proof? No such rule, right? There's no such rule as negation. The only time you are allowed to do negation is when? Negation of conclusion and double negation. So you can double negate something, but you cannot do any kind of negation on a line like that.
Negate that, you just put parentheses around it and a negation outside the parentheses, correct?
Yeah, or I could just do that. So that would be double negation, and that's legal. So I can always put two nots in front of something. All right, so now we have little cheat sheets for direct proofs, and we have cheat sheets for indirect proofs. You know, like we have our list of rules that we want to use. So are there any other questions about formal proofs? So if you use those rules, you should be able to get pretty far in a proof. So try not to get stuck. That's the worst thing. And what's the other thing that you shouldn't do?
This class.
Missing class is very bad, yes.
Overdo it.
Memorize rules.
Memorizing the rules is not the main thing in this class, right? I want you to be able, if you could write a whole proof and not put the rules, I'm only going to take off a limited number of points for that. Because if you really understand the rules and don't necessarily know what the names of them are, that's not as bad as not being able to finish the proof, right? Because eventually you could learn the rules or you could look them up. And that's why I give you the rule sheet during the test and any time that you need it. So the most important thing is to...
Just don't write junk down.
Right, don't write junk down. That was the main thing. So don't look at a proof and just start writing anything that you know. Go back to your steps, especially for direct proof. You want to look at what you're trying to prove. Find things that will help you prove it. So you don't want to be writing down anything that you know is true for no reason. So have a reason for the steps that you do and you won't waste your time. Okay, the next thing that we did in class was the logic circuits. So in logic circuits, we really only used two kinds of gates. And what were they? And or. So I've just told you that implication is the most powerful tool for formal proof, but in logic circuits, we usually use ands and ors. So if we were going to build a circuit for an implication, we would have to use or gates. The reason for that is because these are the most fundamental pieces. And when you're trying to design systems, you want to understand the most fundamental pieces.
But you could use AND gates as well, because an AND gate is an OR gate.
Right. You could always just use either AND gates or OR gates, because they're logically the same as long as you had what other kind of gate?
Negation.
Not. So I also need NOT gates, or inverters is what they're called. So those are our most important gates. So I can use two of those and make any circuit that I want. That's a complete system. So we had a little secret identity of AND gates, which was what? De Morgan's, right? So De Morgan's for an AND gate tells me, if I said P and Q, what's De Morgan's tell me that's equal to? Not the quantity, not P, or not Q. So if I applied this not to here, I would negate both of the variables and swap the operator. So an AND gate is really an OR gate on the inside with its inputs negated and its output negated. So anytime I see an AND gate, I can think of it as an OR gate, negating whatever the inputs are and negating the output. And the same thing happens with OR, because it's a very similar rule, right? So OR gates are secretly AND gates on the inside with the inputs negated and the output negated. So if you have a question that says, convert this circuit to use only AND gates, you don't need to even write anything down. You can just look at each of the gates, negate all of the inputs and outputs, and then you can swap the gate. So that's De Morgan's with pictures. So we had a really important tool for building circuits. If someone gives me an output function that they want, what was that tool? So if they told me what the inputs were, we had disjunctive normal form. In other words, ORing together min terms for a function in order to generate the logic function. So let's do an example.
Could you show us, like, on the questions that you gave us? You gave us like the circuit first. Then you had us come up with this. Can you show us on how we would do that?
Sure, I'll do that after I do this problem.
Okay.
We'll draw a diagram for this, and then we'll take away the equations, and then we'll derive the equation for it. So on your test, I'm probably not going to give you a function. I may, but I probably won't give you a function right here, f. I'm going to tell you some rules for x, y, and z when I want f to be true. And so you have to fill out the table for f. So I want f to be true whenever, let's say, x is less than y and y is less than z. Sorry, x less than or equal to, and y is less than or equal to z. Let's OR those together. So let's say so I want f to be true whenever x is less than or equal to y or y is less than or equal to z. So if x is small, that's always going to be true, right? It's not going to be true. This will be false in these two cases. So let me check where y less than or equal to z is going to be true. That's going to be true in this case. I just made up this function. It's not good, right? Because this is always true. So how do I generate this function with min terms? Actually, it's not a bad problem to do.
Just
Right?
You have 8 min terms.
I would have 8 min terms. So what is a min term?
Anytime there's a 1 in the function.
A min term is an AND statement that represents the state that my circuit is going to be in of all the inputs. It tells me the values for all the inputs. So what would be the min term for the first row?
Not x, y, and z.
The min term would tell me that x and y and z are all false at the same time, so they're ANDed together. So I would have not x, not y, not z. And those are ANDed together. And it's very important that I have 3 little bars there instead of 1. Right? Because if I had 1 bar, then this wouldn't be an AND, it would be an OR, using De Morgan's. So I would write the min terms for each one of these, and then what would I do with them? I would add them together, and adding is logically equivalent to OR. So I write my min terms, putting a not if I see a 0 in the table. So the function for f here would be this. How many gates would it take? 8.
9.
9 gates, because I would need 1 gate for the OR.
Yeah.
And I have 8 min terms, so I would make a gate for each one of those and OR them together. Yes?
In your equation for f, how is x less than y for, like, when x's are 1s?
I checked the value.
Second part of
X is less than or equal to y. So in this case, let's look at this row. X is less than or equal to y is going to be true because 1 is less than or equal to 1.
Okay.
I just do row by
But
row.
what about the one, like,
Previous. This one?
no, the one above it?
This one.
No, one more up. Yeah, that one.
Well, I have 2 statements. I have x is less than or equal to y, or y is less than or equal to z. So in this case, x is not less than or equal to y, but y is less than or equal to z.
Okay.
I skipped a step of making columns for each of the less than functions, right? I didn't do that. So to make a circuit for that, I would have 8 gates, and each one of them would have
3.
3 inputs and 1 output, and they would all go into a giant OR gate, right? So I'm not going to draw all of those because I think that you all can do that. But I will make an example where we'll just look at the logic circuit and generate the function in just a second. So the first min term was not x, not y, not z. So what do?
Negate.
I
Draw a
put
line
little
to the
circles
end.
here. The little circles stand for what?
Not.
Not. They're shorthand for inverters. So that means somehow before you get to the AND gate, invert the value that's on this line. The other way you could do this is you could say that these are your inputs. And you wouldn't want to knot them, right? You would just say that. I would prefer if you would do the top one. So if you would do the ones with the inverters, because then I don't have to check all these inputs and see if you put the bars in the right places. Because it's a lot easier to check for the little circles, right? Although either one is legal. If I wanted to change this OR into an AND gate, what would I do? So supposing that there's a bunch of other things
Negate
coming
all
in
the
here.
inputs and
I would negate all the inputs, so I would draw a secret AND gate inside. Negate all those babies there. And negate the output. Right, so if I wanted that to be an AND gate, it should have knots on the back and knots on the front.
be tied up in knots.
And then I would, of course, get rid of the OR gate. Now let's do an example of writing a logic function if I make up a function here. So how do we read a logic diagram? We read left to right, right? So we follow the inputs. We see what kind of gate it is. So this gate has what output?
XY.
X and Y, which is written XY. So this input here is XY. What's this input? Z. And what is this? Dot. It's a connector that says whatever's values on this line, send it over here. Okay, so if it's a dot on a line, it doesn't mean negate it. It just means take this and send it over there also. Okay, it's like a little splitter. This little jump here means don't do anything with these two lines. They shouldn't really cross. All right, so this is an OR gate. So before I get to the not, what is the output? So that would be XY plus Z, and then I would negate the entire output. So that's the difference between putting the circles on the back of the gate as opposed to on the front. If they went on the back of the gate, then each of these would have been knotted and I would still have an OR. Now the input for here is XY. This is how I really do these. I follow, before every gate I write down the input, what it is, before it goes in. Before this goes here, it's Z, then not Z is the input before it gets to the gate. Right, so this is an AND gate, so I get XY ANDed with not Z. So the inputs for this gate are the quantity XY plus Z negated, and then I'm going to OR that with XY not Z. So my final function, let's call that F. Say F is equal to XY plus Z, all negated, plus XY not Z. What would you do if I asked you to reduce this function?
Try to factor out.
XY negated. Y and Z.
I would do De Morgan's, and then I would try to factor something out. I can see I probably won't be able to simplify this anymore. That's not very many gates for 3 inputs, right? But if I asked you to, what you would try to do is first do De Morgan's. So I would do that here. I would get XY knotted times Z knotted plus XY. It looks like I can simplify a little bit. How could I simplify that? So I can take XY plus, negated, sorry, plus XY, and then multiply that by not Z.
Ooh, that's 1.
That'd be 1.
X not xy, xy is 1.
That's right, that's 1. I made up a function that turns out to be not Z, right? So this is just 1 because I have a variable ORed with its opposite. So xy is ORed with not xy, which is always true because either xy is true or xy is false. That was good, thank you. So then that just reduces down to not Z. So I would only need an inverter for that circuit.
If we do these with using the not symbols,
That's fine.
it
You can
is-
use the logic symbols also. I usually use the bars because it's a little easier to read when I have lots of symbols.
Okay.
Because in this case, I mean, if I had a lot of different things, this could have been a lot longer here, you know, for this function with the number of gates I have. So it's easier to read if I don't write, if I just use dots or nothing for multiplication for and then use pluses for ors, and then I definitely am not going to confuse which two they are. So we have those kind of problems. We have logic circuits, and then we have what? Should have some predicate calculus, right?
what if they told us to draw the circuit for the reduced form? Didn't you ask us to do that at one time?
Yes.
I never did yesterday.
How do I draw a circuit for not Z?
It's like a new
I would have a Z input into an inverter,
or at least well enough.
and that would be my output, not Z.
And that's equal to the same function as above, right?
This is it, yes. It's equal to the same thing as above. So if you wanted to build an inverter circuit, you could build it with all those gates I had drawn before. That would be
Or just that one gate.
quite redundant, yes, or you could just use that.
Okay.
How could you make an inverter circuit? Let's not do that.
Join the AND inputs.
Hmm?
Are you thinking of joining the inputs of AND? No.
You can make a NOT gate with other gates. Okay, so the next thing was predicate calculus. I want to spend a little bit of time on that. But since it's been more recent that we did that, I won't spend as much time just because I want to give you a few definitions for our next topic, which is another kind of proving that we're going to do. So we're going to be doing induction for several weeks in this class. And induction is very, very important because induction is used to prove statements are true no matter what your input variable is. So if you have a predicate, we're going to be proving that predicates are true independent of the variables. So that means we would be proving what kind of statements?
Tautology.
For all predicates, right? They would be for all statements. I would be proving things like for all n, p of n is true. So I use induction to prove that. Because I can't list every single value of p to make a proof, right? So I'm going to prove it for all, and my universe happens to be an infinite set, I can't write down an infinite number of things. Why can't I?
Infinite is not defined.
A proof for the fact that I can't is if it takes me some finite amount of time to write it, right? Say it takes me 1 microsecond to write down one output. It would take me an infinite number of microseconds to write down the infinite number of outputs, and I'm not going to live that long. So that's a proof. Okay. Predicate calculus. We were just talking about some quantifiers. So we have for all is upside down A, and there exists X. These are called quantifiers because they let us know when a statement is true. So they're quantifying the variables in the statement. So quantify is to give a value to. So we're not actually telling which values are going to be true. We're just going to say how many of them are true. This is called the universal quantifier, just in case you want to sound very logical. This is the existential quantifier. So universal means true for everything. Existential means there is one. There's one that exists. I usually talk about there is one, even though there exists means some. It can mean some also, because it's a little more helpful to assume the worst case, that there's only one true. So we do that a lot in computer science, assuming that the thing that makes a statement true only happens one time, because that would be the worst case scenario, or the hardest one to deal with. So that's why we often talk about that.
Is it at least one?
At least one. That's also what it means. So there exists also means at least one. So remember how I wrote, I was saying something when I read these that sort of translates into almost making variables and making code. So when I see a for all, I say for each x. So if I'm trying to write English statements with these quantifiers, I say for each x. And for there exists, I say I can find an x. And that will help you write English statements, because those are very clear and concise ways of letting me know how many times I'm going to have to look at something. So for each lets me know that that's a loop that changes over all the possible values. I can find one just means that as soon as I find one, I get to stop. Okay, and kids are really good with this stuff, right? You tell them, get me something to write with, but as soon as they find something that looks remotely like it might write something, they're going to give it to you whether it works or not. Okay? But if you say find all the pens in the house, they know. If you tell them, hey, you're not done yet, they know that you're right. My microphone's not working?
This is our intermission, I guess.
Yes, this is an intermission. There won't be any taping of the test in case anybody was worried about that. Except for my individual entertainment. Just kidding.
It's in this class.
Yes, the test will be in this classroom next time.
And we're supposed to trust you that that's true.
Okay, so the next thing I was going to do was talk about De Morgan's with quantifiers, because it's very important. So if I were to use De Morgan's on for all x, p of x, what would that be logically equivalent to?
There's not yes.
If I couldn't do that in my head, I would do double negation and then apply De Morgan's. So I would have written not for all x, p of x, and then done De Morgan's on this. And gotten just, what I do is I pretend this not shoots through, and it switches everything that it sees. And it goes through all the possible things. So it would be there exists, and it also negates p of x. And these are the same here. Okay, so for alls and there exists are kind of like ands and ors, right? I would think of a for all as p of 0 is true, p of 1 is true, and p of 2 is true, and p of 3 is true, and so on and so forth, right? And there exists is kind of like an or. Either p of 0 is true, or p of 1 is true, or p of 2, or p of 3. So these are kind of saying like infinitely ands are true, or infinitely an or is true. Or however large your set is. It doesn't have to be infinite if your set is finite, right? So that helps you. That can help you remember De Morgan's, because we reverse from ands to ors with De Morgan's. We reverse from for alls to there exists with De Morgan's. So how many things, in order to make for all x p of x, how many things do I need to make it false? I just need one p that is false. So it could be p of 10 or p of Tiffany or p of whatever the inputs happen to be. I only need one to make for all false. So in my truth tables with predicate calculus, we have some shorthand that reminds us anytime I see for all x, and let me do a little more complex example here, if I see a 0 for a for all, no matter what the statement on the inside is, that means that there is at least one thing of whatever this is, at least one x that makes it false. Right? So there's at least one false for this entire statement, the entire predicate that comes inside the quantifier. And I wrote it as a more complex one to remind you that it goes with the entire inside of the quantifier, not just the first thing that comes after the quantifier. So everything that it applies to, there's at least one false for this entire statement, not just for one of those. So if it's true, then everything in it has to be true. Remember that we said that for all was like an and. So P of 0 implies Q of 0 has to be true. P of 1 implies Q of 1 has to be true. P of 2 implies Q of 2 has to be true. And so on, so they're all true. So that was our shorthand to remind us of the quantities. When I do predicate calculus, if I put a 0, it has to come under the quantifier. It really applies to the whole statement. The statement's either true or false. The stuff on the inside is a predicate, which is not a proposition. Remember, our definition of proposition is a statement that's true or false. Without a quantifier, I cannot tell if P of x implies Q of x is true. So without saying either x equals 5 or saying for all x or there exists x, I cannot tell the truth value. But I can tell you how often it's true, perhaps. And that's what these are for. This is at least one false, all true. So there exists has rules also, and they're derived, again, from the definition of the quantifier. So if there exists is false, I just put this line just to keep these straight, to know which one. But really, this 0 goes with the entire statement. Now, P of x implies Q of x has to be what? How often is that true if there exists is false? It has to be always false. Right? So if you think of there exists as an or, in order for an or to be false, all the values have to be false. So that can really help you with the difference between there exists and for all. In order for there exists to be true, I need how many to be true? At least one. Why do we do these? So why do we talk about how often these values are true?
So when you add them, when you have to and them all together or them all.
If I want to combine the predicates to make new statements, then I have to understand how often the statements are true. So I want to make a little handy dandy table that I didn't give you before, but you can always derive yourself. I'm going to put these sort of shorthand in an order for you. I'm going to go from most true to most false. So what would be the next? I only have 4 of them.
At least one true.
And then?
At least one false.
At least one false. And then what?
All false.
All false. So this is an order of true to false. Now remember that ands preserve falses. Right? So and sort of is associated with the bottom. And ors preserve trues, so they're sort of associated with the top. So if I were to take 2 variables, so if I did P of x, and I ordered it with Q of x, I'm going to take the highest thing in this table. So if I have all true and all true, it's definitely going to be true, right? All true. If I have at least one true and all true or together, then I will get the things closer to the or. So the highest one closest to the or is the one that you'll get, all true, because it preserves the maximum number of truths. So if I did P of x and Q of x, it will be the lowest value. So if I have at least one true anded with an at least one false, I will get at least one false. Right? What about if I or an at least one true with at least one true?
At least one true. At least one.
I get at least one true. How about at least one false with at least one false?
At least one false.
Oring or anding?
Or.
Oring at least one.
You don't know.
We don't know. So the problem comes if we can't decide, like, OR preserves truths, but in this case, I don't know how many truths there are. So if I have two at least one falses, and I OR them together, I don't know if I get any truths. So there's one more dimension to this table. That's a question mark. If I put at least one false or at least one false. And what do you think might be the other thing I'm going to add to this table?
At least one true and at least one true.
So if I take at least one true and I AND it with at least one true, that also is undecided, because ANDs knows how many falses there are, but at least one true doesn't tell me anything about false. So when I AND them together, it doesn't let me know, because sometimes it might be true, right? So if I say it's true that at least one person in this room has red hair, and it's true that at least one person in this room has on purple, you don't know if the statement that there's a redhead wearing purple in this room is true or not, without examining all the possibilities. So that's why we have question marks for those combinations. Now this is if they have the same variable, right? If both the predicates have the same variable. If they have different variables, it doesn't really matter. Like these things, you will do the maximum of these, but if I have, you had one example in your homework. Since the predicates don't depend on each other's variables, I can act like I can separate these and think of them separately. So as long as I leave them in the same order and just move everything out to the front, that's going to be logically equivalent. So when I do these combinations, I don't need to actually think of the quantified variables. I don't need to think of how often they're true. So these are going to be true no matter what. Because if this were true, say for all x, p of x is always true, then I could think of p of x as always being true and put a 1 in there. And this statement doesn't even need a for all anymore, and that would be a 1, and 1 ANDed with anything gives me the q, would give me the q back. So this statement would just be like saying there exists y, q of y. If this statement were false, then that would be like q of y being 0, because all of them would have to be 0 for the statement to be false, right? So it would be just like putting a 0 in here, which would make the whole thing false.
False. Preserve 0. Yeah.
Right, so then you might have a couple of things where, so if I know this one's true, I really understand this one well. If I know this one's false, this is really easy. So the only thing is the case where this one is false and this one is true, where I might have some confusion, right? So let's say that for all x, p of x is false or 0, and there is this y, q of y, if that were true. Then q of y would have at least one false, right? Sorry, at least one true, and p of x would have at least one false, right?
Okay.
Yeah, it would have at least one false.
For it to be false. So
Because for all x to be
Prove that all true.
false,
If they were all
it's
true,
false.
then it would be true, and it's not true, it's false. So you have at least one false.
right, I have at least one false, otherwise all of them would be true, and this statement would be true. So in this case, I would have at least one false for p of x. So what I would do is I would sub in one false here. Because I would say there's at least one false for p of x, so I'd put a 0 there for p of x. And then I would say this statement in the inside is false. And then the for all can't possibly be true. Right? So for all can't have any falses on the inside. So I would break it down by case and try to substitute for the variables and if I have two separate variables. And you can always do this. It doesn't matter. If you have separate predicates with separate variables, you can move the quantifiers to the front. It's just like doing variable definitions in a program. Right? If one variable definition doesn't depend on another one, you can move all of them to the top of the program. Right? But if one depends on another one, I can't just move them anywhere. Like if one depends, like if it's inside a loop, I can't just move it up to the top. So So we need to be able to do truth table proofs, and I just talked about doing one without actually doing one, but let me remind you how to do one. So when I see a truth table proof, my propositions I can fill out just like regular. So I'll put 0, 0, 1, 1, 0, 1, 0, 1 for those and combine them with an AND. Then I would use my definitions of my quantifiers to find out how often the predicates on the inside were true. So if this is false, then I have all false for P's, and I have at least one true in these cases. And I can fill these out on automatic. Oops, I need a column for that. So you already got, most of the credit for this problem just by doing that. At least half of it. Then I have to figure out what happens when I AND P of X and Q of X. So all false ANDed with all false gives me all false. All false ANDed with at least one true gives me at least one true ANDed with all false. All false again. And at least one true ANDed with at least one true. We don't know because AND preserves falses and I don't have any falses to preserve. So I'm not sure about that one. So this could be either 0 or a 1. The rest of these have to be false because if I have all falses for P of X and Q of X, then there aren't any X's that make P and Q true. So then I have to check the implication between the first column and the second column if I label them.
Is that an implication or?
It's a logical equivalent, so I want to see if they're logically equivalent,
Okay.
which obviously they're not now, right? So let's just figure out which way this will go. Which way does it go?
Point.
That way.
It goes from 2 to 1, right?
Yes.
Because zeros can imply anything, but ones can't imply just anything, right? So a 0 or a 1 can imply a 1 because implication's true if the conclusion is true, right? So this is the best way to go. It's going to go that way. It'll be all ones if I go in that direction.
What if it were under 2 if it were P of X or Q of X instead of and Q of X?
Then that would actually go both ways. Right? It would be logically equivalent. If this were an or, then I would have an at least one true right there.
But it would change your all falses too, wouldn't it?
No?
No?
Well, it might. Yeah, I would have a 1 there and a 1 there. But this would be, I guess if you put an and there, so it wouldn't be logically equivalent. Right? But the implication would go this way. Right? So what he was asking is, if I change this to an or, what would happen? What would happen in this case is I would have an at least one true right there, right? Which would give me a 1. And this would give me an at least one true too, which would give me a 1. And then the implication could go from the left to the right, from 1 to 2. So if it were an or statement, you could fill out the truth table for that too. So even if you're not sure what I'm talking about right now, you can do it, I'm sure.
Third one also going to be at least one true.
Yeah.
Line 3.
Is that at least one true?
If it were an or, it would be at least one true in that case, which would give you a 1 in the last row.
What about the third row? Same thing.
Instead of an and.
The third row. Is it the same thing? At least one true?
Yeah,
It will
that's
be.
right. It's at least one true also. Okay, so those are all the items. If you look in Packet 2, it has a first hour exam study sheet that reminds you of all the topics that you need to know. It also has some first hour exam review questions with answers with sample solutions, so please look at those. It has some sample proofs for you to do. If you want to practice doing some truth table proofs, proving that statements are true, then you can take your axiom list and prove those by truth table. All of them are provable by truth table because that's how they were proved in the first place. So those are all good ways to study. You can also look at the special test packet, which is online on the website, and try to do all the problems that are related to logic, set theory, logic and predicate calculus and circuits.
Those answers are not, solutions are not posted, right? For the special
No,
test?
there are no solutions posted for any of them. Tomorrow, there will be a study session from 5 to 7 in the office.
And what about multiplexer?
It's gonna be on there.
No. You'll have a design problem, but you won't have to reuse a gate that you design.
Sessions in your office in January, right?
So, thank you.